Okay, so I guess we're there. So let's get started. So, well, gosh, what an influence John had on my life. There I was, a fledgling philosopher, trying to interested in mathematics. And John, through his writings in the got a long time ago, in the 1990s, gave me the confidence to think that you could get access to the forefront of mathematical and scientific knowledge through his writings. I mean, what a joy that was to engage with his writings back at that time. Huge influence on me, and a bunch of people will know that we started a blog together a while ago. We had a lot of conversations over a great many years. So it's a great pleasure to have him speak to us here today on applied category theory. So thank you, John.
Well, thanks very much. Thanks for inviting me here. The influence was reciprocal. It's really exciting to think that what one is doing in mathematics could actually be interesting to a philosopher, so that one isn't just like fiddling around with obscure equations. So I want to talk about applied category theory, which is the latest turn in this game. And I'll talk more about the history of the subject and what people are trying to do than any mathematics per se. I've given lots of talks about the mathematics, and so have all the people who I'll be referring to here. So it's certainly easy to click on any of the links in my slides and get into the actual mathematics, but I'll try to not say as much about that as I sometimes do. So we often have this picture of different disciplines or subject areas talking to their neighbors, and information flowing between pure math, which is at some very abstract end, to, say, the business world, which is maybe at the very concrete end, in stages, with each discipline talking mainly to its neighbors. So pure mathematicians talk to applied mathematicians, they give suggestions to applied mathematicians, and they find out about problems from applied mathematicians and learn techniques from applied mathematicians. And similarly for each link down the chain, with each discipline talking to its neighbors. And in this model, which of course is very oversimplified and you can easily find a lot of faults in it, in this model, we could think of category theory as the purest of pure, some super pure mathematics that only can talk to mathematicians, who then relay their insights down the chain to the other more practical subjects. I think that's what a lot of people implicitly feel about category theory, or at least used to. And so when people started talking about applied category theory, people laughed because it sounds like an oxymoron. It just goes completely against this picture here. However, I think this picture is inaccurate. For one thing, a very important fact is that starting maybe around 1980 or so, it became clear that computer science really cuts across this traditional flow of information. Computer science interacts almost directly with every single piece of this chain. Computer science has a big relation to category theory, which I'll explain, but it also has a huge relation to other aspects of pure mathematics and applied mathematics, and so on, down to business. So businesses will need to keep abreast of developments in computer science, and so on. Basically, we now communicate and think with the help of these machines called computers that we have devised to help us, and they change the whole game at every single step of the way. Now, I have this crazy idea that maybe category theory actually really should be thought of in a somewhat similar way, as interacting with all the different links in the chain from the pure end to the applied end, rather than being tucked away at the super pure end of the spectrum. Now, at first, this seems ridiculous or laughable. I mean, for starters, category theory is sort of nothing compared to computer science. Everybody's walking around carrying cell phones. Well, nobody has even heard of categories by comparison. So category theory is an ant compared to the elephant of computer science. However, I'm thinking about what could be, not what yet is. And secondly, when you think about how computers have unified the whole chain, it's done so by means of the internet, which is an enormous network. And category theory is nothing if not the mathematics of networks, or the science of networks. It's other things too. I shouldn't have said it quite that way. I mean, it is the science of networks, but it does many other things too. So to really devise good methods of getting computers to do what we want, we need a way to think about them. And I think category theory is one of the important ways to think about them. So you may think this is ridiculous still, because, for example, if category theory was talking directly to business, you'd expect that people would be going into business doing category theory or something like that, setting up category theory businesses. That sounds sort of silly, but in fact, it's true. So in fact, people are setting up category theory businesses. And that's part of the kind of thing I want to talk about. I want to talk about how category theory is now being used at all steps along this spectrum. And for that reason, my talk will be less focused on the math than on the history of how category theory became applied, giving you a flavor of how it's being applied, and pointing out some of the challenges that show up. Before I dive in, I should say that this history is going to be extremely self-centered. I am not really in a position to write a good or talk about a good history of category theory. So hopefully someone who eventually tries to write a history of applied category theory will listen to this talk and fold it in as one data point. I'll talk about a lot of people, but I will also leave out a lot of people, and I really apologize to all the people whose work on applied category theory I'm not mentioning. There's just no way for me to do a fair treatment of this big subject. Okay, so I'll start arbitrarily in 1963 when Bill Levere introduced a concept called Functorial Semantics. So it's a very general concept where you have a category that describes syntax, describes ways of writing things down, and then you describe the process of interpreting those expressions or giving a meaning to those expressions via a functor. So the functor will send expressions to their meanings. But a crucial aspect of this whole setup is that there's not one God-given functor f that does this. You can choose various functors from the category C to various other categories G, because there are different ways to assign meanings to expressions, and that flexibility is very important. And it became important in computer science. So for example, there's a way to think about it where a sufficiently well-behaved programming language may give a category where you think of the objects as types or data types. We've already heard about that idea. So types, X, Y, Z, etc. And then a morphism between objects, like a morphism F from X to Y, we think of as a program that accepts data of type X as input and outputs data of type Y. And then the fact that you can compose morphisms tells you that you can hook up two programs to get a bigger program where the output of the first program becomes the input of the second. And that combination is a program in itself. So I could say that like the relationship between the lambda calculus, which is sort of an idealized programming language, simplified programming language, and Cartesian closed categories understood by Lambeck is an example of this paradigm of using functorial semantics for computer science. But here I'm only so far talked about the category C. I haven't talked about the functor. So what the functor could do, well, we could, for example, take a functor from our category to the category of sets, map each data type X to a set and that would be the set of possible values of that data. So like you could have a data type like real numbers, and then F would map it to the actual set of real numbers. And then each program gets mapped ideally to a function. And the key fact of a functor is that it preserves composition, so that composing programs would give rise to composing the functions they compute. And the identity program, which does nothing at all, you interpret it via this functor f, it gives you the identity function, which does nothing at all on a set. So that's a paradigm that became important in theoretical computer science. I wouldn't say that most computer scientists know or care about functorial semantics, but in a certain community of the more mathematical theoretical computer scientists, this idea has become quite important. And there are certain languages like Haskell, for example, and others that really take advantage of this viewpoint. In particular, Haskell uses a category theoretic construct called monads, which has sent many generations of young computer scientists running for help from category theorists to try to figure out what a monad is. I don't want to explain what a monad is. It's a category theoretic construct, which, like many other constructs, become important when you start thinking about programming in this functorial semantics way. But in the 1980s, something very different happened. Particle physicists realized that any quantum field theory specifies a category, and now the objects are, roughly speaking, collections of particles, and the morphisms are, roughly speaking, ways for particles to interact and turn into other particles. And in fact, Feynman drew pictures called Feynman diagrams for describing how particles interact with each other. This was a bold move because, although it seems very intuitive here, you have a proton and an antiproton coming in from the left, and then they collide and all sorts of other particles shoot out. In reality, particles are not little dots moving along little straight lines. Quantum mechanics says that particles are wave-like in character. So when Feynman introduced this pictorial language, he got a lot of opposition from older quantum physicists like Heisenberg and Bohr. And yet it turned out Feynman was correct in doing this. What Feynman diagrams actually are, later became clear, much later, is there are pictures of morphisms in specific categories, and that each individual quantum field theory gives a category, and then that determines what allowed Feynman diagrams you can write. So if you have a theory that doesn't have quarks in it, you're not allowed to write this Q line for quark. And then what do you do with these pictures? Well, your goal in particle physics is to compute a bunch of numbers, like what's the probability that if I smack two particles into each other that some other particle shoots out. So for calculating numbers, we need to interpret our Feynman diagram. That is, in the functorial semantics attitude, we need to functor from our category to some other category which assigns meaning to the Feynman diagrams. And this category we could take to be the category of Hilbert spaces, a widely loved mathematical structure in quantum mechanics. And so then this functor will turn any Feynman diagram into a morphism in the category of Hilbert spaces, and that's called a linear operator between Hilbert spaces. And so you can look at what physicists are doing with Feynman diagrams as basically using them as a syntax, which they then apply the semantics to then grind out numbers. Now, Feynman probably would have laughed at this whole business because he knew what he was doing. He didn't need any category theorists to tell him what he was doing. But by the 1980s, particle physics had become elaborate enough and deeply connected with enough pure mathematics that this attitude of thinking of quantum field theory in terms of functorial semantics became a really profitable attitude. You could do things with category theory that particle physicists were struggling to do without category theory, and so it helped. And this led to a whole line of work trying to relate category theory to quantum mechanics. And in 2004, Samson Abramsky and Bob Kricka wrote a very influential paper showing that a certain quantum process that goes by the name quantum teleportation, and also other quantum processes could be understood using category theory and using diagrams that resemble Feynman diagrams. But here, the edges in these diagrams, which now I guess we're reading from top to bottom rather than across, the edges are not describing elementary particles, but just states of an arbitrary quantum system. So it could be an electron or it could be some larger system. And I don't want to try to explain this in detail, but these are pictures of morphisms in some category, and they're equal to each other. And these morphisms describe some process where one participant, who always is called Alice in cryptography, communicates a message to another participant, who's called Bob. And in quantum teleportation, you have the superficial appearance that you're communicating faster than light. But in fact, what's really going on is that you've laid the ground for the communication by some classical process that has already transferred some information, and then the rest of the information is transferred on the basis of that. In any event, quantum teleportation was a sort of magical, wonderful thing that you can do in quantum mechanics, and this gave a kind of category theoretic account for how it's working. And that was quite exciting to people because it took the quantum applications of category theory out of the realm of elementary particle physics and into a new realm that was developing, which is quantum information theory or quantum computation, which has the potential for being a quite practical thing. And indeed, already quantum cryptography is used. So on the basis of this and other work, and also on the basis, I should say, of a huge amount of charisma, Bob Kirka and Samson Abramsky built a huge group of people at Oxford, sometimes called the Quantum Group, working on category theory, the foundations of quantum physics, and quantum computation. One interesting thing about this enormous group here is that it's in the computer science department. So not a mathematics department, not even a physics department, but a computer science department. Here's Samson Abramsky here, and here's Bob Kirka looking sort of disreputable over on the edge. That's completely intentional. He's like that. And here are many, many people, including I see Jules Hedges, who was mentioned in the previous talk. He works on categorical cybernetics. So Kirka and co-authors developed this diagrammatic method for explaining quantum physics. And they eventually decided it would be very good to write a textbook on this. And so here is one of the two textbooks that Bob Kirka helped write on pictorial methods of understanding quantum physics. And the one interesting thing about this book, so first of all, I recommend this book if you're interested in learning category theory from an unorthodox and sort of easier approach than the conventional one, because it's very pictorial. But I mention it because part of what you wound up doing is hiding the category theory in the sense that you don't run around saying category and functor and all sorts of other jargon like that a lot. Instead, you draw pictures of processes and you explain these pictures in a hands-on way, and you explain how you can stick one picture onto the other, which is composing morphisms, but you don't say the word composing morphisms necessarily because you don't need to. And this is one of a generation, I should say, a new generation of category theory textbooks that are part of the applied category theory movement. So if category theory is going to reach directly to many different communities at different stages of the knowledge chain that I drew at the top of the talk, it means that you can't force people to first become mathematicians before they then start doing things with category theory. The traditional approach to category theory treats category theory as like some finishing school that you engage in after you've already learned abstract algebra and this and that, and algebraic topology and so on. That's just too onerous a path to category theory if you're trying to get computer scientists, much less business people, to get some inkling of category theory. And it's not really necessary to take that elaborate route, because category theory is something so fundamental that it can be explained more directly. I especially recommend Eugenia Cheng's book, The Joy of Abstraction, which is a really wonderful introduction to category theory for people who have not had much prior exposure to mathematics at all, and it goes all the way up to the Oneida embedding theorem. So in 2021, Kirke actually left Oxford University, and he became the chief scientist of a company called Quantinuum, which uses category theory for quantum computing and also natural language processing. This is a picture of him on the Quantinuum webpage. As you can see, he's trying quite hard not to fall into the stereotypical academic image here. He's a great guy, by the way. You shouldn't mind me teasing him like this. I think, though, that it is important that having people with personalities who are willing to break out of the stereotypical mold of a math professor is important in this whole category theory application movement. I should say that there's a lot of interaction between quantum computing ideas and natural language processing ideas, which I won't really have time to get into. To some extent, they were visible in the last talk, but if you want a real emphasis on the natural language processing aspect, the works of Ty Dene Bradley are very good. She's another newer explainer of category theory to non-category theorists, and she is also working in a company that uses quantum methods and categorical methods for natural language processing. But functorial semantics is extremely general, so it's not just applicable to the topics that I've already mentioned. So in lots of areas of science and engineering, people use a syntax where you draw diagrams, and then a semantics where you convert those diagrams into math, which is very often the systems of differential equations. You're describing how things change in time. You're describing dynamical systems. So you use differential equations. But the interesting part is that hooking up diagrams to each other is actually composing morphisms in a category. And the fact that you're working with functorial semantics says that when you compose those morphisms in the syntax category, your functor will map it, the resulting composite, to the composite of the two systems of differential equations that each picture separately is mapped to. So in other words, there's another category lurking around here where the morphisms are actually systems of differential equations. Systems of differential equations with some specified inputs and outputs to serve as the source and target of your morphism. Here are some different pictures. You've seen a bunch of these types of pictures, I hope. So electrical circuit diagrams are one of the earliest and very widely used. This thing here is called a Petri net, and it's a Petri net of a particular model for the AIDS virus and its interaction with blood cells, infection of white blood cells. This here is a very small diagram in the subject of control theory, where you have some process that in an industrial plant that you're trying to keep under control. And so you take feedback, you read off information from that process, and you use it to feedback, affect the process itself to keep it on track. I mean, the very simplest example here would be like a thermostat, but in industrial chemistry, they become much more elaborate. And so there's a whole diagrammatic language of control theory that you can read about in textbooks on that subject. And this is a little diagram of some molecules in molecular biology. In molecular biology or biochemistry, they have so many different diagram languages that in fact they've set up a committee to standardize the diagram languages so that people reading different biochemistry papers can look at the diagrams and not have to be explained each time what the diagrams mean. But it's sufficiently baroque that that the committee wound up choosing 3 different diagram languages because they need multiple languages to describe different things they're interested in. So these are very widespread, and the people in these different subjects don't think of what they're doing here as category theory. They don't think of it as mathematics. They think of it as, this is the stuff we draw to understand the differential equations that you can convert these pictures into. The equations are the math, but these pictures are our own private little trick for understanding what's going on. But I claim that these pictures are actually also mathematics. These diagrams are morphisms in various categories, which are using functorial semantics to convert to differential equations. So I decided that had to be true, and I wanted to work out the details around 2012. So I asked Brendan Fong, who eventually became my grad student, to tackle what I thought would be a very good first example, namely electrical circuits, because everybody knows about electrical circuits and the mathematics of them is in some sense very well understood. Linear electrical circuits, for example, made out of just resistors or maybe capacitors and inductors as well. I asked them to create and study a category having open electrical circuits as morphisms. So these are electrical circuits which have certain things hanging out which serve as inputs and outputs. I think in the last talk they were called cilia. So these are just these dots here. So he took forever to do it, so it seemed, but it turned out that what he was doing was not just answering the question that I asked, but in fact, answering a much more general question. He invented a general theory, which he called decorated cospans, for handling this problem, but also all the other problems that I described. That is essentially all the other kinds of diagram languages I showed can be understood using the theory of decorated cospans, although the details have to be individually worked out in each case. This decorated cospan formalism is a recipe for getting categories of this general sort. And so naturally, it did take him a while to do a good job of it. And he finished his thesis on it in 2016. I won't attempt to explain decorated cospans any more than I just have. I've given lots of talks on decorated cospans, and you can see on YouTube me giving talks about them if you're interested. I just want to mention one little thing is that, well, first of all, here's Brendan Fong, and here's another student of mine, Blake Pollard, who together with Brendan applied this theory of decorated cospans to the second example that we tackled, which was Markov processes. So Blake did a lot of work on Markov processes. And another thing I want to mention is that Brendan went to get his PhD at Oxford, so he was in the enormous group that I mentioned of Kirka and Abramsky, and I believe Kirka was his de jure advisor, but in fact I was the de facto advisor talking to Brendan about this problem, and so nonetheless it's really important that this large body of people at Oxford is spreading across the world, doing many things, and Brendan is one of them. So after doing his PhD, Brendan went to MIT in 2016 to work as a postdoc with David Spivak. So Spivak is another very important figure in applied category theory. So among other things, he had helped to create a language for databases called Functorial Query Language, which has now become the basis of a company called Connexus AI, with Ryan Wisniewski as a head of that company, but David Spivak also involved. This approach to databases really relies heavily on functorial semantics. So the idea is that a database schema is an object in some category, and that by a functor you can map it to a sort of populated or inhabited database schema where your table of is actually filled with entries. You can imagine like taking a spreadsheet and actually typing in the entries. That's one possible interpretation of the abstract database that has not yet been interpreted with specific people's names and numbers. And in 2014, David wrote a textbook on this idea and others called Category Theory for the Sciences. So I also highly recommend this as yet another of this new generation of category theory textbooks that's trying to reach out beyond the traditional confines of the category theory community of highly pure mathematicians toward other audiences. And in 2018, Brendan Fong and David Spivak wrote another textbook explicitly on applied category theory, which is fondly called 7 Sketches, but its actual title is longer, emphasizing the principle of compositionality in many guises. And they taught a course on it, which you can see on YouTube if you click on this link in my slides. And the textbook is also available for free on the archive, as well as for purchase. And I'm mentioning this stuff about things being available online for free, partially because when you're trying to reach out of the pure math realm into the rest of the world and teach the rest of the world category theory, you quickly realize that making things easily available for free is going to speed up the process a lot. And so I think there's a general commitment so far on the part of a lot of applied category theorists to make things open source and easy to get at. Now, in 2018, my graduate student, Kenny Corser there, and I came up with structured cospans, which is a simpler alternative to decorated cospans. Turns out to be not quite as flexible as decorated cospans, but in many cases, either formalism works. And in those cases, I'd say structured cospans are simpler. In 2020, Christina Vasilikopoulou, who's standing to the left there, helped us understand how decorated and structured cospans are related. For a while, I thought structured cospans would replace decorated cospans, but it turns out we now see that they can't cover quite as much territory and that we really need decorated cospans in some cases. So the full story is somewhat elaborate right now, and I've given talks about that, but it's actually very pretty. So by now, structured and decorated cospans have been used to study open systems of many kinds. So by open systems, I mean systems that have loose ends, that are meaning systems that are morphisms in a category that you can stick together or compose to get bigger systems. And open graphs are just simply a graph with loose ends. It's a very combinatorial structure. That's a very simple example. Open Petri nets is a more useful example. Here's a picture of an open Petri net where you have things describing they're called places. They could represent like populations of different kinds of chemicals or organisms. And then you have these blue boxes called transitions, which describe how things can come out of various places and turn into things of other kinds. If you attach numbers to these transitions, describing the rate at which the transition tends to occur, you get something called an open Petri net with rates, or maybe an open chemical reaction network with rates. And my student, Blake Pollard, worked on those. Open electrical circuits, I've mentioned. Open Markov processes, I've mentioned. Open dynamical systems, those are the systems of differential equations interpreted as morphisms in some category. So there are papers on all of these, and if you click on these brown things, you'll get to those papers. So at a certain point, I thought that maybe someday all of this would lead to some unified language of the sciences. And my ambition, which seems very limited in retrospect, was that by interacting with scientists, maybe eventually this unified language would help scientists in one discipline talk to scientists in another discipline and share tricks of various sorts. But then something quite different happened, which is much more exciting in my mind. Namely, in 2019, James Fairbanks, who's an engineer, and Evan Patterson, who is a statistics PhD, began developing a computer system called Algebraic Julia it's a system for high performance scientific computing built on the language called Julia, which is designed for crunching numbers really fast. But Algebraic Julia lets you program using constructs from category theory. So in Algebraic Julia, you can talk about categories, functors, and all these other things that category theorists like to talk about, and write your programs using those concepts. So it's a very, very high level system, but coupled to the raw computational power of Algebraic Julia. So they were trying to revolutionize scientific computing in this way. And in 2020, Evan implemented structured Cospans in Algebraic Julia. And then using this system for the example of open Petri nets, he and Mika Halter reconstructed some of a COVID-19 model, which was currently being used by the UK government. So the UK government had a very elaborate model of COVID-19 with many populations of different people with different conditions, possibly living in different locations, etc. And then, the populations are these orange boxes, and able to turn into other kinds of people via these transitions in blue. The whole model is much larger than this. This is just a tiny fraction of it. And what they wanted to demonstrate was that you could build the whole model by building smaller models in pieces and then subsequently sticking together those pieces, which is in fact something that had not been done before. Models were had to be constructed whole cloth essentially by one person keeping track of the whole thing. But this was a new approach, compositional epidemiology. And so it attracted the attention of some epidemiologists, especially since COVID-19 was a very live issue at the time. Then, in a different direction, in 2021, Brendan Fong and David Spivak, who had been, remember, over at MIT, decided to quit traditional academia and start their own institute called the Topos Institute in downtown Berkeley. It's an institute for applied mathematics, but with a heavy slant on applied category theory. And they hired a number of people, including Evan Patterson, and also Sophie Libkind, who's here, who will appear later in the story. And it's a real incubator for ideas on applied category theory now. And so this is another one of the sociological moves that had to be made, I think, to bring applied category theory forward. I recommended Brendan not try to start an institute right after his first postdoc, but luckily he was much braver than I would ever be, and he went ahead and did it, and it's quite successful now. So in 2022, Sophie Libkind, Mika Halter, Evan Patterson, James Fairbanks, and another person I haven't mentioned, Andrew Boss, used Algebraic Julia to systematically build models of epidemiology using open Petri nets with rates. So here are some open Petri nets, the rates, that is the number data is not being shown here. And here they're being stuck together to form a larger open Petri net. The way that they're being stuck together, you'll notice, is not end to end. This is not the normal end to end composition that you see in a category. This is something a little bit more general. We're sticking them together using a trick called an operad. So operatic composition is one of the things that they incorporated in their algebraic Julia software, which is, so this previous work was done in a slightly ad hoc basis, but this really used operads in a systematic way. And then in 2022, also, another team of people, including myself, used algebraic Julia to create software for building models of epidemiology using another style of diagrams called open stock flow diagrams. Well, stock flow diagrams, but we're making them open. So here are some of those kind of diagrams being stuck together in an operatic style that is not end-to-end, but sort of gluing them all together to form a bigger model. So part of the point here is that when we started talking to actual epidemiologists, we applied category theorists learned more about how they actually want to do their models. And they didn't really want to do their models using Petri nets primarily. They wanted to use a different technique that they considered congenial, called stock flow diagrams. So in fact, there's a community of epidemiologists who use stock flow diagrams to model the spread of disease. And it includes my co-authors, Nathaniel Osgood and his grad student, Xiaoyan Li. And one crucial fact is that they did COVID modeling for the government of Canada. So they were requested by the government of Canada to set up COVID models for a number of different provinces. And in the process, they gained a lot of experience with stock flow models. They already had a lot of experience, and they wouldn't have been asked to do it, but they gained a lot more experience, and they learned some of the problems of the existing technology. There's a beautiful thing about stock flow diagrams, which is that with just a little bit of training, you can read them and you can understand what they're talking about. So a fellow named Hoffman has pushed the idea of community-based modeling, where you go to a community that has some problem, like a disease or some other type of problem, and you help model it, and you model it by drawing stock flow diagrams, which here are hanging on the wall in a room in rural India. And then people can look at those diagrams and comment on them and help you improve the model, because these people, the local people, they will have the knowledge of what's actually going on that the modeler who just flew in from Oxford or wherever may not have. And here we see a woman here looking at the picture on the wall, and this is actually from a story where this woman noticed that some ingredient was being left out of the model that these village elders hadn't known about or hadn't thought about, and so she helped fix the model. So that's the example of what you can do. And you notice that none of the people in this story here had to know category theory, but they were in fact drawing morphisms in a category unbeknownst to themselves. Now, most stock flow modeling in the commercial level or the government level is done using a piece of software called AnyLogic, which is very powerful, but it has several big problems. It doesn't let you compose models. It lets you make a model, but it doesn't let you take a bunch of models and stick them together. It doesn't separate syntax from semantics. It only has one semantics, namely the differential equation semantics, which is the most important semantics, but there are others that you would like. It has no support for what's called stratifying models. That term was very confusing to me. It's sort of jargon in this community. What it means is taking a model and splitting one stock, one type of group of people, into several stocks. So for example, you might have a simple model, and then you may say, oh, we should subdivide people according to age groups, because older people get the disease more than younger people or something like that. And you would like your software to make it easy to do that. It had no support for collaboratively building models. It's basically one person as the software and they make the model. They could talk to other people, but they're the one who's building the model. And it's not free, it's a commercial piece of software, and it's not open source, so people can't get in there and modify it and improve it. So our new work aimed to fix all these problems. And I could say we're well on the way to fixing all these problems. So the reason it's so important to compose models is that the models that get actually used in the real world are immensely complex. So here's a picture of Osgood and Lee's COVID model. This is a page in AnyLogic, the software. This is the whole model. As you can see, it's an enormous web of stocks and flows and such. And you really would prefer actually not to have to deal with this whole entity at once. You prefer to have it be thought of as being made up out of smaller pieces, because mentally it is made up out of smaller pieces. But that's not captured by the software, unfortunately. AnyLogic just doesn't do that for you. So we've now created software that does that. It supports compositional modeling with these stock flow diagrams. So it's called stock flow. And if you click on this link, you'll go to GitHub, which is where computer programmers keep their open source software. So you can download the software. And so it lets you create and compose open stock flow diagrams and lets you stratify them that is, subdivide stocks into smaller stocks. For those of you who like category theory, I'll mention that that's done using a technique called pullbacks in category theory. It lets you choose among several different semantics functors, so one of which is the differential equation semantics. And of course, it lets you solve the differential equations once you get them. And then Nate Osgood and another student of his, Eric Redekop, went further and made a graphical user interface for StockFlow. So StockFlow was written in this programming language called Algebraic Julia. To interact with it, you needed to know Algebraic Julia. But this graphical user interface called Model Collab, it runs on a browser, and you manipulate the model by actually dragging and dropping little boxes and drawing little edges between boxes. So, and because it runs on multiple browsers, teams of different people located in different locations can collaborate to build StockFlow diagrams. So I could build my piece, you could build your piece, we could both save them. They'd be saved on the cloud. I see there's this little thing called cloud here. Oh, that's not what it's actually for, though. Sorry, that's a mistake. But you can save. Nate's gonna laugh at that. Actually, clouds are these little funny things here. But you can save your models on the internet, and so that other people in different locations can access them and then glue them together to form larger models. So in the goal to really apply mathematics, there are many levels, because the next step is to actually train epidemiologists to use Model Collab. So we have some things going for us. So first of all, Nate Osgood runs regular training sessions, which goes by the quasi-militaristic terminology favored in computer science of boot camps, because they're supposed to be intense. So he runs boot camps on epidemiological modeling. So he is beginning to teach people Model Collab. Second, no understanding of category theory or the programming language Julia is required to use Model Collab. So it's really crucial when you're applying category theory that you can ultimately black box the category theory, and so that people do not explicitly need to know it to use what you're creating, although they may be using it in some kind of implicit way. And third, it's free, while any logic you have to pay for, which should ultimately be an advantage. But I should still say it will take a lot of work, because when you have a generation of modelers trained to use any logic, this new paradigm is not so easy to shake. So as I just already said, applying mathematics takes many steps. And as I've moved from being more of a pure mathematician towards a bit more, at least some days of the week, of an applied mathematician, I realize how easy pure mathematicians have it. You just write a paper, you explain your idea, you throw it out there, and you hope that somebody reads it. But when you're trying to actually carry out the full application of an idea, you have to interact with many people with many skills, persuade many different communities that what you're doing is actually worth doing. And it's a much more elaborate, but I should also say very satisfying endeavor. So I'll conclude by saying that applied category theory is interesting in many ways, some of which I hope will be interesting to philosophers. So some of these ways are separate from sort of the core mathematical ideas. So one thing, as I hope I've illustrated here by my somewhat self-centered history, is that it requires new forms of communication and collaboration, because you're talking to new types of people. And luckily, these are starting to come into existence. So there's an annual applied category theory conference that's first started in 2018, run that time by Brendan Fong and some of his other young friends. Another is a journal. So there's a journal called Compositionality, which is again started by Brendan Fong and some of his young collaborators and friends. This is an open access, free to publish, free to read journal of applied category theory, which I recommend to your attention. And another is called the Category Theory Community Server, which is sort of like a chat site or a discussion site for applied category theory, actually for all category theory, but it has a lot of applied category theorists there. This was initiated by my grad student, Christian Williams. And so these are different ways for category theorists to start talking to other kinds of people, people who might want to apply category theory or learn category theory. And I hope that these catalyze the process that I'm trying to outline here. Another thing is that category theory raises ethical issues in ways that category theorists aren't used to. Pure mathematicians tend to feel themselves somewhat insulated from a lot of ethical issues because although their math may get used for all sorts of purposes, they don't consider themselves particularly responsible for how their mathematics gets used because it's so abstract that they sort of can blame someone else for understanding it and doing something with it. But when you start doing explicitly applied category theory, that sort of veil of protection is ripped open, and you see that what you're doing may have a fairly immediate effect. So, for example, the biggest funder of research on applied category theory is currently the US military right now. And also, a lot of applied category theory is being used for artificial intelligence or machine learning or large language models or so on. So I'm not saying that those are necessarily bad things. I'm saying that those are things that definitely raise serious ethical issues. And so I'm worried about the danger that applied category theory will wind up merely intensifying the already existing patterns in society. That is, it will only make the richest and most powerful people even richer and more powerful. I would prefer it if applied category theory could do something really different, really new. This is one reason why I've tried to focus on epidemiology, which is a little bit different than some of the other applications. Of course, even epidemiology ultimately feeds into the healthcare system, so there are questions about that as well. I would really like to use applied category theory for environmental issues, but I haven't quite gotten there yet. Anyway, I just wanted to emphasize that ethics is the provenance of philosophers, and this is a really interesting intersection of mathematics and ethics, which I hope that people think about. And another thing applied category theory does is revitalize what is a very old question: which mathematical structures are best for describing and designing systems? I emphasize designing because with the rise of computers, whatever you can think about clearly enough, you can make. So it's not merely describing the external world, you're also making worlds based on your descriptions. And so with this immense freedom that you have in computer science, the question is what should guide you? And it opens possibilities for some really radical progress, because these are some really brand new ideas that we're talking about here that may let us organize systems in new ways. So I think there's a lot to think about here, and I hope some people here give it a try. Okay, I think I'll declare it done.
Brilliant. Thanks ever so much. You can see why I got drawn in by him 30 years ago. His ways of conveying ideas so clearly. Okay, let's have some questions then. Let me bring up the people. If people online have some questions, they can raise a hand, and I hopefully should be able to see. Or anyone here? Okay, Mark's got a question.
I do have a question, and I'm finding stuff that thanks for that, by the way. This is really exciting stuff for me, but I'm wondering if I'm biased and reading too much into this, that just works in my self-interest. I do philosophy of time, and I'm one of the few people who defend the notion that time flows. And I see in your work, but maybe it's through these biased eyes, that this project is bringing back the idea of thinking of differential equations, for instance, as things that flow, that functions are something that flow. And I noticed the importance of diagrams as and these diagrams are reminiscent of what organizations would call flowcharts. And I'm wondering whether I'm reading too much into this as something that might be an answer to the static view in maths that came out of set theory and thinking of functions as something that is static and doesn't flow. So I'm wondering whether or not I'm reading too much into it. So maybe that's the question.
Sure. Yeah, the question of static versus dynamic is, as you know very well, a extremely tricky question, because I could take any dynamical system, and when it's done, or when we imagine it as being laid out in time, then we can think of it as a static thing, with time as just another space-like dimension. And I think it's very hard to like definitively break out of that. But nonetheless, category theory is a generalization of set theory, in a sense in which, instead of just having elements in a set, you have objects and also morphisms, and the morphisms are meant to convey some kind of dynamic aspect of the system. That is, a morphism goes from an object to an object, and that's a very primitive sense of dynamics there, of the start and the end, and it brings a kind of dynamical quality to the foundations of mathematics, which is a real thing. It's not just an illusion. I mean, even though you could, if you ask a traditional mathematician, what is a category, and they're saying, oh, it's a set of objects and a set of morphisms and some functions doing this and that, right? So you could say, oh, we're just back in the same old paradigm. And that's what I meant by it's hard to definitively break out of that paradigm. I think it's more, in some ways, more of a question of attitude rather than anything else. And anyway, I think the interesting thing about the differential equations here may be, the interesting new thing, maybe the study of open differential equations, which are differential equations where some quantities are explicitly labeled as affected by the outside world, affected by the part of the world which is not modeled by the differential equation. So traditional differential equations, well, no. Physicists often like to study what are called autonomous systems of differential equations, where you know everything there is to know once you know the differential equations. Whereas open differential equations, which I should say are also studied by physicists and especially engineers, have certain quantities which are not determined by the differential equation. They're regarded as being affected by the outside world. And that on the one hand allows you to treat systems of differential equations as morphisms that you could stick together by sticking some of these quantities on the edge to some other quantities on the edge. But it also means that you're not just dealing with a deterministic system in the classic sense anymore, because you have quantities that are affected by the unknown. So it definitely changes your attitude towards differential equations.
Thanks. We got a question from Toby.
It's not so much a question, sorry, although I would love to. I mean, there's lots of questions I could ask, but I need to head off because I actually have to go give this talk again just now. So thank you very much for inviting me, and I hope the discussion is profitable.
Okay, thanks, Toby. I had something that interests a lot of people around here is the difference between when you get variables that are just sort of associated with each other, some kind of statistical association, versus when you think there's some kind of causal connection between them. You might think you can get a much better grip on the world if it isn't just association data, but there's you've got that A causes B. Are there ways of getting at this through your or is it that I guess the modelers are kind of coming already with their sense of what causes what, and or is there any way of representing the difference?
Yeah, so this particular line of work that I was outlining, as you say, most of my talk was about model building, where you have your opinion about what causes what and how it how X affects Y, and you build the model into that. So there's a flip side of the whole modeling process, which I didn't talk about at all, which is incredibly important in epidemiology, which is inference. So you measure data and you try to establish causality and also various numerical quantities, which you would then put into your model. There's a lot that applied category theory has to offer to that, and I'm afraid I'm not quite as knowledgeable about that. I will say that Brendan Fong, for his master's thesis, worked on a categorical approach to Bayesian networks, and that has subsequently grown into things like what Toby was discussing, and so that's also part of the big story. And another part of it is that there's a technique called particle filtering, which is widely used by epidemiologists, where once you have one of your models of the sort that I've been discussing, you run it, and you run it a bunch of times, and you see what kind of outcomes it predicts. But then you use that to compare to reality, and you use that to estimate the parameters that should be in your model. So I guess what you could say is that, like, what I've been describing was just sort of one half of a feedback loop of interaction between modeling and then comparing model with reality, and yeah, so the whole thing should be carefully understood, and I'm afraid I have sort of focused on one half of it.
Sure. Yeah, I've seen various diagrammatic techniques from category theorists and trying to get it kind of causal modeling. I mean, that exists out there, doesn't it?
Yeah, it does, and that's important.
Okay. Well, I think there's no further questions, and we've reached 6 o'clock anyway. So let's just. Oh, sorry, was there one? There was one. Sorry, there was Dominic's. Go on. Here you go.
Yes, sorry, I'm casting around. I have lots of things to say. I'm sort of trying to formulate them into questions difficult. Hi, John.
It's Dominic.
So one thing that I know in computer science is quite a big deal is sort of algorithms and data structures, and kind of getting the right data structure for the right task to get good performance, and I think there's a lot of things that category theory has to say about this, kind of describing data structures in a more abstract way, sort of polynomial functors and things like this. What I haven't quite sort of understood is how much of that kind of work is going on in the applied category sort of movement recently, sort of linking with back with computer science, the sort of like programming aspects around what I would call kind of classical computer science, sort of algorithms and data structures. Do you know if there's much of that going on within the sort of ACT world, or is that largely more back with the computer scientists?
So the algebraic Julia community is really trying to blend computer programming with category theory in a really rich way, so that you can write software and you can say, define functor, blah, 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 define pre-sheaf category, blah, blah, blah. So that's just one of several different initiatives to try to bring category theory into programming. So not just have it help programming it, but have it actually be part of the programming. So that's one thing. There are lots of other things, and I probably don't know a lot of the other things. So I will just mention again this company, Connexus.ai, uses categorical approach to databases. So it turns out that updating databases is very nicely described using categorical ideas like font extensions. And Mike Johnson in Australia has been serving as a consultant for database companies using category theory ideas for many years. But now this company, based on David Spivak's work, is also doing that. And there are a lot of other things. I should say that there's just a lot more on the computer science side that I'm not very familiar with.
Okay.
All right. Thanks.
Okay. Thank you very much. Okay, so well, here we've reached time. So what we have to do is thank John very much for his very interesting talk.
Thanks.
So I've recorded this session, and we can. You said you were thinking of putting it online. We can
yeah, I'd like to if that's acceptable.
That makes sense. A nice intro. Yeah. Let's do that. Good.
All right.
Okay. Well, thanks ever so much, John. And,
okay. Thanks very much.
Bye everyone online.
Bye.
I'll see you.
See you then. Bye.
That's the couch.